Hey everyone, and on behalf of Forge College, welcome to this explainer on state and storage mechanics. Now, in our previous lesson together, Execution Model Deep Dive EVM versus SVM, we looked at how these virtual machines actually process instructions, right? Whether that's the EVM doing it sequentially or the SVM running transactions in parallel. But execution doesn't just happen in a vacuum. Every single transaction leaves a footprint. So today, we're looking at state. It is essentially the inevitable memory of that execution. How do these networks actually remember what just happened? Well, let's find out. Okay, let's dive into this. Here is our structural blueprint for how we're going to tackle this. We'll start with an intro to state mechanics, look at storage representation, explore what I like to call the two cities metaphor, stress test some real-world scenarios, examine persistence and snapshotting, and finally, wrap it all up with key takeaways. So, starting off with Section 1, Intro to State Mechanics, and what actually dictates these operations. Now, you might be wondering, why are we talking about this immediately after execution models? Well, simply put, execution dictates what kinds of state operations are even possible in the first place. Think of state as the literal memory of a blockchain. It's the atomic unit of persistent data. It bundles together an account's identity, its balances, its executable code, and its storage. Now, if your execution is serial and single-threaded, like we see in the EVM, your state can rely on relatively simple global structures, because only one thing is changing it at a time. But if your execution is parallel, like the SVM, your state representation has to be entirely different. It absolutely must support concurrent access, isolation, and explicit conflict detection. Moving on to Section 2, Storage Representation, let's look at the architectural blueprints. We're going to look at the foundational blueprints of how the EVM and SVM actually map out their data. So, in the EVM, an account identity is just a simple 20-byte address. The SVM, on the other hand, relies on public keys and program-derived addresses with very explicit owners. For code, the EVM stores a hash separately, while the SVM explicitly splits the program from the data. Crucially, though, the EVM relies on a flat key-value map of 256-bit slots for persistent storage, whereas the SVM uses structured, typed account data. And, because of this fundamental difference, the EVM uses uniform reads and writes, while the SVM demands explicit borrow rules that are strictly enforced by the runtime. The practical implication here is literally huge for developers. The EVM gives you a minimalist universal primitive. Those flat 256-bit slots are incredibly expressive, but man, they are completely unforgiving. You have to manually manage your data layout. The SVM is basically the opposite. It's a structured, rule-heavy data owner. It pushes structure and ownership directly into the runtime itself. So it's much safer by default, but it definitely requires a completely different mental model to build on. Which brings us to Section 3, the two cities metaphor. Let's try visualizing this architecture. If you're finding these architectural concepts a bit dry, this is where it usually clicks into place. Imagine the blockchain's global state as a city. EVM City is basically a giant infinite parking lot. Every smart contract gets a parcel, and inside that parcel is a grid of absolutely identical parking spaces. These are your 256-bit slots. You park your data by doing math to compute exactly which space a variable goes into. It's totally uniform, which is great, but if your math is slightly off, you just accidentally parked two cars in the exact same spot and one of them is completely crushed. SVM City, however, is a collection of fenced compounds. Each program gets a compound with labeled rooms and storage closets. And there are literally bouncers at the door. The runtime actively checks ownership and prevents anyone from entering a room without explicit permission. You can't accidentally park in the wrong spot because the bouncer simply won't let you in. So that's the static view. But what happens dynamically? What actually happens when a transaction moves through these cities, trying to change things? To understand the dynamic flow, especially for a parallel execution, we really need to talk about two specific things, the read set and the write set. The read set is simply the state that your transaction inspected or looked at. The write set is what your transaction actively attempted to change. When transactions are running concurrently, the runtime looks at these sets to figure out if two transactions are trying to bump into each other in the exact same room at the exact same time. All right, Section 4, Real-World Scenarios. Let's start stress testing these concepts. Now, what's really interesting about this next part is seeing exactly where storage mechanics will either break your code or totally save it. We're going to look at three concrete scenarios: storage collision bugs, failed transactions with partial writes, and node snapshotting and reorgs. First up, storage collisions. In the EVM, if you were building an upgradable contract, say you're using a proxy pattern, you compute a slot using Kashak 256 math. But if you pack other variables into low index slots and your math happens to overlap, a read operation will return an entirely unexpected value. And it's a total nightmare because it silently corrupts your contract semantics. In the SVM, because of those fenced compounds we talked about, the explicit program-owned data regions, silent collisions are drastically reduced. The runtime maps distinct accounts to distinct regions. However, you do still have the headache of carefully managing invariance across different accounts, so it's not totally magic. Next up, failed transactions. In the EVM, this is a very linear process. Transient writes happen during execution, but if the transaction reverts, the VM just discards those changes entirely. Poof, they vanish. For developers, this means you absolutely must test your revert paths. In the SVM, it's a totally different mental shift. Transactions run speculatively. If two transactions conflict, meaning their write sets overlap, the runtime aborts or reorders them based on their dependencies. You aren't just thinking about a linear accept or discard. You actually have to actively design your transactions to minimize overlapping write sets so they survive that speculative execution. Which leads us to Section 5, persistence and snapshotting. How do these chains handle reorgs? Let's zoom out from the smart contract level for a second and look at what happens at the network node level, especially when things go wrong. The underlying state structure completely dictates how a node handles chain reorganizations. The EVM uses authenticated data structures called Merkle Patricia Tries. These are great because they allow for very compact proofs. If there's a chain reorg, the EVM just reverts to a previous try route. It's very clean. The SVM, however, handles snapshotting by aligning with its ownership model. It uses whole account transfers and chunked snapshots. Rollbacks are managed at the account or ledger entry granularity rather than just pointing to a global route. So why does this matter to you? Well, it matters because this underlying persistence model dictates exactly how long it takes for a new node to sync to the network. It impacts how efficiently light clients can verify data. And if you're a developer building an off-chain dashboard, an indexer, or any kind of tool, this defines the exact invariance you can actually rely on when requesting state proofs. It is absolutely crucial stuff. And finally, Section 6, takeaways and next steps. Let's get to the actionable rules. Let's bring this explainer to its practical conclusion. If you're transitioning between these environments, here are your actionable rules of thumb. Number 1, in the EVM, you must manage your slot layout and packing with extreme care to avoid that silent corruption we talked about. 2, in the SVM, you must design for parallel execution by intentionally minimizing overlapping write sets. And 3, universally, always test your revert paths for the EVM and your concurrency aborts and retries for the SVM. Ultimately, the size and the shape of your writes directly impact your storage costs and the performance of the entire network. Large, messy writes to broad namespaces increase persistence sizes. Tightly scoped writes keep state lean, which is way friendlier to parallel execution and honestly much cheaper for your users. You absolutely must choose storage patterns that deliberately balance cost, proofability, and how easily nodes can sync your data. To wrap up, I want to leave you with this provocative thought. How does the shape of your state dictate the ultimate cost of your runtime execution? Think about that as you architect your next application. On behalf of Forge College, thank you so much for joining this explainer. To dive deeper into this subject and really master more Web3 concepts, be sure to visit us at forge.college. And stay tuned for our next lesson, Architectural Differences and Runtime Constraints, where we're going to see exactly how these storage patterns literally slam right into compute budgets and memory limits. See you then.